Hi, and welcome back to another video on equilibrium, this one on Le Chatelier's principle. All right, so we talked in class about what Le Chatelier's principle tells us, and a system at equilibrium, if it is disturbed by a particular change in concentration, maybe temperature, or a change in pressure, that equilibrium system will try to counteract the change that you are making in order to reestablish an equilibrium. So we're going to look at an example. We've got a bunch of different changes here that we're going to make to the equilibrium, and we will determine either if it will shift towards product side to the right or shifting to reactant side to the left. All right. This is a very typical question that you're going to see either on a quiz or a final, and it's definitely something that you're going to want to know for your upcoming test. All right, so this is question 14 from your workbook. It's on page 35. If you want to reference it there, you can. There are several examples in your workbook for Le Chatelier's principle. So after this particular one, definitely recommend trying a few of those yourself. So here's our equilibrium. Carbon monoxide plus water is in equilibrium with H2 hydrogen plus CO2 plus heat. That's telling me something. Plus heat. All right, let's do the first change. CO2 is removed. So if I look and see, CO2 is a product in this particular equilibrium, so I am removing that product from this equilibrium. When that happens, the equilibrium is no longer at its state of balance, right? It's now less on the product side. There are less products than what it requires to be in equilibrium. Equilibrium doesn't like that. It says, whoa, hold on. I need to make more CO2 in order to replace the CO2 that was taken away, that was lost. If I'm removing a product, the equilibrium will shift to the product side to make more and replace what you have taken away. If I add H2O gas, so H2O gas is right there, this is a reactant. I'm now putting in a whole bunch of more reactants into that equilibrium. So we have our balance. It's now heavy on the reactant side. Too many reactants. The equilibrium doesn't like that. It's like, wow, hold on. Got to get rid of all of those reactants that are now extra into my system. How does it get rid of the extra reactants? Well, it tries to make products. It tries to make more products to balance the extra reactants that you are putting into the system. All right, so we're going to use all those extra water molecules, and we're going to make more product that's going to shift to the right. Pressure. If I change the pressure, either increasing or decreasing, in order for a pressure change to occur, or sorry, not to occur, to have an effect on our equilibrium, there has to be at least one gas in the equilibrium. Now all of these are gases that you can see, so that's fine. There has to be at least one gas, and there has to be a different number of moles of gases on the left side and the right side. So if I look at this particular equilibrium, yeah, something is not looking right. Hang on now, this does not look like it is balanced. I think I'm missing something here. 1 carbon and 1. I got 2 oxygens. Oh, maybe it is balanced. 2 hydrogen and 2. Oh, no, it is balanced. I'm sorry. I thought it wasn't balanced for a second. Okay, so everything is balanced. There is gas, at least one gas molecule present. In order for a pressure change to have an impact on an equilibrium, there has to be a different number of moles of gases, left side and right side. If I count my moles of gases, I have 2 moles on the left side, and I also have 2 moles on the right side. So because they are equal, there is no change. I'll say NC, no change for that particular pressure increase. Yeah, maybe that's not the best example to show. I'll show one after of a difference in pressure where there is a different number of moles. Okay, temperature is increasing. When there's a temperature increase, you have to know if your equilibrium is endothermic or exothermic in order to decide which way it's going to shift. So coming back to our equilibrium, we've got this plus heat as a product. The plus heat is telling me that that is exothermic. So heat is a product of that particular reaction. I am going to increase the temperature. I'm increasing the temperature. I'm increasing the product side of that particular reaction. The amount of heat goes up if I'm increasing the temperature. In order for equilibrium to reestablish, it's going to want to use that extra heat and get rid of it. How does it get rid of that extra heat? By shifting to the reactant side. So we're going to go in the opposite direction of the heat. Volume, a lot of times you're going to see pressure changes, but asking about volume, because you need to know that pressure and volume, right, are indirectly related. So if the volume is going down, that means the pressure went up. And we've already decided that because there was an equal number of moles, there is not going to be a change for that particular item. Okay, so no change for volume decreasing. Catalyst. A catalyst doesn't actually affect the equilibrium, except that it would make the equilibrium occur quicker, right? Just like a catalyst does, but it's not going to cause a shift in any one direction. So no change when you add a catalyst. If I add hydrogen, so this time I'm adding a product. Now my equilibrium is out of balance. I added more hydrogen. My product side is heavy. The equilibrium doesn't like that. It's going to want to use all these extra products in order to reestablish equilibrium again. How does it do that? It tries to make more reactants. So it's going to shift to the reactant side. And then the last one is CO removed. I'm taking away that reactant. So here's my balance. I'm low on the reactant side now. I need to reestablish equilibrium again. How do I do that? By making more reactants, right? To bring it back to its equilibrium state. So I'm shifting to the left side towards the reactant side. Okay, let's just do a little, a second example here, because that one had an equal number of moles of gases on either side. So this is a very common equilibrium reaction, nitrogen plus hydrogen in equilibrium with ammonia. All these are gases. Okay. Now you can see from this particular reaction, I'll move it over here so we can have a good look at it. If I look at the number of moles of gases on the left side and right side, they should be different in order for a pressure or a volume change to actually have an effect. So if I count my number of moles on my reactant side, I have 4 moles of just gases. That's important. If you had a heterogeneous equilibrium with solids, liquids, aqueous, gases, whatever, you're only counting gas molecules, so that's important to note. On my product side, I have 2 moles of gases. When you have more mole of a particular reactant or product side, more moles indicates more, molecules in that particular space. So if I have more moles, more molecules, I'm going to have a higher pressure because there's less room for these particular molecules to move around. So my higher number of moles is equivalent to a high pressure side. The lower number of moles is equivalent to a low pressure side. All right, so I am going to increase the pressure of this equilibrium. So pressure is going up. The equilibrium, again, it doesn't like that. You make a change, it's going to want to do the opposite. So if I make the pressure go up, the equilibrium is going to want to make the pressure go down. How does it do that? By going to the side or shifting to the side that has less pressure or less numbers of moles. So if you're making the pressure increase, we are shifting to the product side in this case, to the lower number of moles. Okay, and you may also be asked about a volume change, so that's important to note here as well. What if I make the volume increase for this particular equilibrium? Again, you have to kind of keep in mind that pressure and volume are indirectly related. So if you're making the volume go up, essentially you're making the pressure go down. If I make the pressure go down, the equilibrium is going to try to do the opposite and make the pressure go up. How does it do that? By shifting to the side with more pressure. So it's going to shift in this case to the reactant side, to the side with higher number of moles of gas molecules, our higher pressure side. Each of those changes are something that you're going to be expected to know how to answer on your quiz and on your final exam. So definitely try some of the workbook questions. I think there's probably 5 or 6 examples with multiple changes in each equilibrium. So definitely give those a try. Make sure you have a good understanding of how each change will affect the equilibrium and what side it will shift to in order to counteract the change that you're making. All right, as always, if you have any questions, be sure to reach out via email or ask in class. And thanks for watching. Bye.